Good afternoon, good morning, good evening. So thank you very much to join us again. But we are here today to attend the talk by Gustavo Wilke, that now is working with Synopsys in Hillsboro, USA. Who don't know, Hillsboro is very close to Portland, and Hillsboro is also the location of the main facilities of Intel. So, Professor Dr. Gustavo Wilke is talking today about analysis and optimization of mesh-based clock distribution architectures. So, Gustavo has a computer engineering degree and a PhD degree in microelectronics from PG Micro at Federal University of Rio Grande do Sul, Brazil, and he's currently a software engineer at Synopsys in the formal verification team. Since 2010, Gustavo has been working on multiple CAD tools in the areas of physical design, power distribution, clock distribution, time analysis, and formal verification. Besides of the industry experience, Gustavo has also over 50 publications. Also, Gustavo also has worked with Intel for several years. So thank you very much, Gustavo, to accept our invitation. And the floor now is with you to start your presentation.
Thank you, Professor Hayes, for the introduction. So this presentation is about the work that I did during my PhD. So I apologize that the slides may be slightly outdated, and I may need some refreshing sometimes. But I was taking the introduction time to go through it, and I think I got it covered. So okay, so the presentation talks about how we can analyze and optimize clock meshes in clock distribution architectures. So let's see here. Okay. So the slides will be divided as follows. So I will start by giving a brief introduction on the clock distribution problem. Then I will give some background, talking about some related works and also some techniques that are used in clock design. I will talk about the clock mesh analysis problem. Then I will present two proposals to optimize clock meshes. Okay, so as everybody knows, the clock is probably one of the most important signals in any synchronous system. It's responsible for synchronizing the propagation of data in the design. And it has very tight time constraints that need to be followed in order to compute the correct data and store the correct data inside each sequential element. So we need to define the clock period carefully so that it accounts for propagation times through the sequential elements, the propagation time through combinational logic, and setup time for the sequential element that's going to store the data. So besides of that, we also need to consider the fact that the clock is not an ideal circuit. It may present clock skew, and the clock skew also has to be considered when defining the clock period. So let me talk a little bit about some of the characteristics of the clock signal. So the three main things that we talk about when we talk about clock, besides of the period, of course, is the clock skew, clock jitter, and clock slew. So in the scope of this work, they were defined as the clock skew being the maximum difference among the clock arrival times at all clock sinks. The clock jitter represents the clock uncertainty. So it's the statistical variation of the clock arrival time over the clock sinks, and the clock slew is defined as the maximum transition time for the clock signal. So in some other works, there may be other definitions for skew, and skew could be considered only for in between the time difference in between the sequential elements that are connected through some combinational path. But for simplicity in this work, we are considering skew as the maximum difference overall arrival times. Okay. So the clock timing is affected by variability sources, as you may very well know. So those variability sources, they come from two different sources. So one is the process variability. And if we don't really account for the process variability when we are fabricating our chip, we may have our yield impacted. And we will see the process variability as being a permanent change in the delays of a given chip. And the other source of variability is the environmental variability, which is a type of variability that depends on the operation of the chip. And this also comes from various sources, such as the supply voltage variations, also referred to as the IR drop, crosstalk, and temperature variations. So those would be the three main sources. So, and the impact that this variation has is, in some sense, harder to deal with because it happens from cycle to cycle. So this is what causes, for instance, the clock jitter. So although we may expect the clock to arrive at a certain time, and we may actually calibrate our models to the impact of process variability, that doesn't mean that the clock will arrive always at the same time. So depending on the operational condition, we may see variations in those delays. So this is the main motivation for the use of clock meshes. So they are able to filter out the impact of process and environmental variations. And this is due to the multiple reconvergence paths that it adds to the clock network. So if one of the paths of the clock network arrives earlier than another path from the clock network, then the structure of the clock mesh will try to balance that delay difference out, and it should filter out the changes in the delay. And it would in the end lead to a smaller clock skew. So the contribution of the work that I'm presenting here is that it summarizes the strategies used to design high-performance circuits, the clock network for high-performance circuits. It shows some data comparing different types of clock architectures. It proposes a simple and effect algorithm to enable simulation of large clock meshes, and propose two strategies to optimize the clock mesh. So I wanted to talk a little bit about different strategies that are usually applied to clock design. So I divided them into 4 different categories. So the first one that I will talk about is related to strategies to improve the reliability. So one of the strategies that is commonly seen on clock networks is differential signaling. So the idea of differential signaling is that instead of encoding the signal in just one wire and encode the signal as a difference of voltage in a wire with respect to ground, we can encode the signal as the difference of voltage of a differential pair. And the biggest contribution of this methodology is that any noise source that would impact both sides of the differential pair would not be seen in the end of this strategy. So this is a technique that is usually used at the highest level of the clock network. It is expensive because instead of having just one wire, now we need to route two wires through the circuit. So it cannot be used in the lower levels because those levels, they have much larger routing. But it's not 100% foolproof. If the noise source affects just the one side of the differential pair, it would still show the impact of noise in the output of the differential network. Another strategy that is commonly seen is shielding. So the idea of shielding is that you want to protect your clock signal from crosstalk aggressors by tying the signals adjacent to the clock network to ground or VDD. And by doing so, you would reduce the impact of crosstalk in the clock delay. And also you would reduce any potential glitches that crosstalk could cause to the clock signal. So the shielding, it can be done, it's usually done only in the same layer. So if you have the wire going horizontally, you would shield only the adjacent tracks, so that you are protecting the largest coupling, since the top and upper layer are going to run in the perpendicular direction. But for some signals, it might make sense also to make shielding that would extend to the top and bottom layer. The main problem with that is that this is very greedy in terms of using routing resources, and it would cause trouble to the routing step to be done. Again, this is a technique that can only be applied at the highest levels of the clock network, and that's actually where it makes more sense, because those levels, they tend to span through larger distances, and they don't need as many resources as the lower levels. So there are also techniques that are used to reduce the power consumption of the clock network. One of those techniques is the clock gating. So clock gating basically means that if we shut off a module, some block in our design, we can reduce power consumption by stopping the clock for that module. So that's going to save the power of the clock network, but also the power of the switching activity inside that module. So clock gating is a simple concept, but it's not so simple to implement. It requires careful consideration of timing, so that the enable signal arrives early enough to block the clock signal in the clock tree. Another technique used for low power is the reduced swing. So that would mean that instead of transitioning our signal all the way through the full excursion of ground to VDD, we would use reduced supply for the clock signal. So by doing that, we would reduce power consumption in the clock network. But it also comes with the price of making the clock more sensitive to noise. Okay. So there are multiple ways we can design the clock network. There are multiple architectures. So the most common ones are clock trees and clock meshes or clock spines. So clock trees, they started traditionally as age trees, which were basically routing topology that would guarantee same wire length from a clock source all the way to each clock sink in the design, given that the sinks would be symmetrically distributed. So later, this evolved to custom algorithms that are able to design clock trees with symmetrical wire length for asymmetrical loads. So two of those algorithms would be the DME, deferred merge and embedding, and the MMM algorithm. So they are probably the best way today to design a clock network, making sure that the wire lengths are kept the same. So besides of clock trees, we can also use clock spines and clock meshes. So clock meshes, they are basically a mesh of wires that we connect to the sink of a clock tree. And that mesh of wire provides us with redundant paths and actually short circuit paths between the output of all those clock buffers, which has a tendency of averaging out the delays at the sinks of the clock tree. So a clock spine would be the same as a clock mesh. The only difference is that a spine usually is one-dimensional. So it's easier to be designed when we don't have the freedom of placing buffers in any place. For instance, if you are designing the floor plan of your circuit, and you need to distribute the clock to a module that you don't have the freedom to put buffers over the block, maybe doing a clock mesh would not be an option. So you can do clock spines in the periphery of the block, and then just route the signal from the clock spine to the clock sinks inside the module. So that would be the main advantage of the spines. They are easier to fit in the design for being one-dimensional. So those techniques, they can actually be all combined together. And when we do that, we usually break down the clock distribution network into different stages. So in a higher level, we have the global clock distribution that would contain some carefully designed clock tree that tends to be very robust to noise, and will deliver the clock to each one of the blocks in our design. Inside each one of our blocks, our IPs, we might have a local clock distribution that may be either a clock tree or a clock tree plus a clock mesh, or a clock tree plus a clock spine. It depends on what are the timing constraints for the block. At the root of each one of those blocks, we may perform a technique which is inserting the skew buffer, which is a buffer with a tunable delay that can be used to compensate for process variability. After the chip is fabricated, the skew buffer is tuned to make sure that the delays at each one of those clock roots is equalized. Okay. So clock meshes, they are usually used inside very high performance designs such as microprocessors. They have very tight performance requirements, and therefore they require low skew. In the literature, there are multiple processors that use clock meshes, and that if you look for those papers, you will see what's the architecture that they are using, how the clock meshes are being used. So usually the distribution follows kind of what I just described a couple of slides back. So we start with a global buffer clock tree that is delivering the clock to all the IPs where we have the regional clock distribution, and that would be where the clock mesh will probably live. And connected to the clock mesh, we have the last stage of the clock network, which is going to be a local clock tree that may be wire length matched, or simply just minimum wire length routing, connecting the sinks to the clock mesh. Depends again on the designer decisions. So the greatest advantage of the clock mesh, as I mentioned, is the ability to reduce clock skew. So this table shows some comparison between the maximum skew seen in a clock mesh versus the maximum skew seen in a clock tree. And it also compares the power consumption in the two scenarios. Sorry. So what we can see here roughly is that the clock mesh can provide much smaller skew, but it comes with the price of paying a higher power consumption. So so the largest power consumption, it comes for not only the extra wire length that the clock mesh requires, but also because the clock mesh creates short circuit currents that will also increase the power consumption. Another advantage of the clock mesh is that it can also reduce the clock jitter, which is something that is highly desirable because jitter changes from cycle to cycle. So it also impacts the guard bands that need to be added to the clock period. So here is a simple experiment showing how much of the clock jitter we can reduce for a given input uncertainty and for two different sizes of clock meshes. So in this case, we can read the table as if we apply an input uncertainty of 3 picoseconds for the clock delay at each one of the mesh buffers. This is going to be the output uncertainty for a 8x8 mesh, and this is for the 16x16 mesh. So again, we can see the huge benefit in terms of performance of a clock mesh. So the main motivation for my work was that clock meshes are used in a lot of high-performance designs, and we lack solutions to analyze and optimize those clock meshes. So the greatest challenge to analyze clock meshes is that the reconvergent paths that create the short-circuit currents that are the core for the performance benefit that's provided by the mesh is hard to simulate. Basically, they create electrical equation that is hard for the electrical simulators to simulate, and also to model the whole clock network requires a huge number of elements. So there are several works that try to tackle this, because we need to have a very accurate arrival time estimation. Otherwise, we may underestimate or overestimate the clock skew, and in both ways, this is a bad thing. So we need smarter and actually targeted techniques to analyze clock meshes. So let me talk a little bit about how we want to do this. So we need a model so we can simulate it. So a simple way of doing that is modeling the wires as a pi model, with a 3-pi model, where we model the coupling through capacitors. The wire resistance will be modeled by a resistance distributed across this line, and we may also put some inductance there. So each one of the clock sinks that connect the clock mesh will break that wire into smaller segments, and then therefore increasing the total number of elements that need to be simulated. So the work that I have contributed to is called the sliding window scheme. So this is an idea that is trying to reduce the number of elements that we need to feed the electrical simulator in order to have an accurate but slightly faster simulation of the clock network. So we can think of the extreme case where you can take a clock mesh and say, look, I don't want to break my wires, and I will just lump all my clock sinks and put them in the crossing points of the clock mesh. And if we do a model like that, the number of elements in our clock network would be greatly reduced, and the simulation time, the electrical simulation time of a clock mesh would be much smaller. But we would have a very coarse delay estimation. So we wouldn't know the impact of the local clock network, and it wouldn't give us enough precision to be able to estimate the clock skew properly. So what this work is proposing is that we create a window of accuracy inside the clock mesh, and inside this window, every element is going to be modeled in the most accurate way as possible. So we are going to break the wires, connect the clock sinks to those wires, and create the pi models for each one of those clock sinks. And outside of that window, we are going to lump all the capacitance and connect that to the crossing points of the clock mesh. So the fact that we are lumping those elements is going to add in accuracy. So the solution we found for that was to create a border around the window, inside which we will have a more accurate model of the clock mesh, but we won't be measuring the delays of those elements. So the inaccuracy lives in the boundary of the window, so we are basically discarding that and trying to measure delays only for the inside part of this window. Okay, so this is a study showing what's the impact of applying this technique with a border around the accuracy window. So we can see that the maximum delay estimation error is drastically reduced, and we are able to get much more accurate delays. At the same time, the use of the sliding window technique allows us to speed up the total simulation time. So this is a comparison of the runtime. So we can see the runtime if we simulate each one of those windows separately versus the runtime of simulating the oh wait, I'm misreading this data here. So this line in the top is the total runtime of each one of the simulations, and the line in the bottom is the maximum runtime for each one of the windows. So what this is actually showing us is the benefit that we might get from parallelizing the simulation. So the main contribution of this technique is to enable the electrical simulation of large designs, to enable a parallel simulation of the clock mesh, and while introducing negligible error. So there are other works in the literature that came around the same time. I won't go into the details here for the sake of time, but those other works, they were proposing techniques such as mod order reduction or other changes to the electrical simulator to try to speed up the simulation of clock meshes. So although they are very interesting works, they are kind of harder to implement because they would require a specialized electrical simulator for the clock mesh. So let me skip through those slides. So yeah, this is the comparison. So the main advantage of the sliding window scheme is that we can implement that using any electrical simulator, and we can handle large clock meshes, and we can parallelize the simulation. The other works that I skipped through, some of them, they present a greater speed up, but at the cost of requiring a specialized simulator, and sometimes it's not providing such a good accuracy as this technique. Okay, so now that we talked a bit about the analysis, let me talk about the optimization. So since we can now simulate and analyze the clock mesh accuracy, we can try to optimize it. So there are works in the literature that try to optimize the design of clock meshes by sizing wires, but they usually assume that the clock mesh is in a condition where the clock is arriving at the same time on every clock buffer, and this is not a realistic assumption. So clock skew could be as large as 20% of the clock period, and this would impact drastically the behavior of the clock mesh. So yeah, here I'm talking about those two related works. I won't go in detail for interest of time. I think I'm already short on time. So let me talk about the technique that I'm presenting in my thesis. So as I mentioned, the previous works, they were ignoring the clock skew at the input of the clock mesh. So what this work is doing differently is that if we consider that the clock doesn't arrive at the same time at every clock buffer, we end up seeing a short circuit current that will flow through the clock mesh. And that short circuit current is going to be responsible for, first, the compensation effect of the clock mesh that will make the faster buffers go slower and the slower buffers go faster. But it will also produce a large power consumption, and it may also have a larger clock slew. So this chart here shows a comparison of how much of the power consumption is coming from the charge and discharge of the capacitance of the clock network and how much would come from the short circuit inside the clock mesh. So in the x-axis, we can see what's the input skew applied to the clock mesh. So as we increase the input skew of the clock mesh, not surprisingly, we see increase in the short circuit current, and it becomes dominant very fast. So that shows that to optimize the clock mesh, we want to tackle the short circuit current. So the first strategy that I've proposed in my thesis was to size the clock buffers according to the nominal skew that they would present. So if we have 3 clock buffers and we can compute among them what's the average arrival time for the clock signal at each one of those clock buffers. So if we take the clock buffers that are either arriving too late or too early, so in this case, we will have A, which is arriving probably pretty close to the average arrival time, B is arriving early, C is arriving late. So if we simply take those buffers that are farther away from the mean and we reduce the size, we are able to achieve an improvement in the clock skew and also in the clock slew. And besides it has the added advantage that we are downsizing the buffer, so it will reduce the power consumption of the clock network driving the clock mesh. So this is another experiment that shows what's the impact that we see in the slew and the skew when we size the buffers. But in this case, we are making a model that is a little bit more pessimistic because it's adding resistance in between the outputs of those buffers. So we can see, and also the larger the resistance, the smaller is going to be any benefit that we would get from this technique. So, okay, so I just talked a little bit about the sizing of the mesh buffers. So after I talk about that, I will also talk about a proposal to design a new type of mesh buffers. And both of those techniques, they are trying to optimize the short circuit current. Okay. So usually the mesh buffers, they are going to be sized according to the load that it's present in the vicinity of the buffer. But as I mentioned, we might be able to take advantage of nominal skew and try to undersize the buffers that would either try to push the mesh to switch early or switch late. And we want to have simply the buffers that are closer to the mean arrival time with the nominal size. So there are 2 sizing algorithms that were proposed. One that is assuming that it's sizing the buffers based only on the mean of the arrival time, so assuming that we have only a nominal delay estimation, and another one that treats the delays as probability density functions and tries to size the buffers according to that. So this is the flow in which this would be applied. So we would generate the clock mesh, generate the clock tree, characterize the clock network, and then apply the resizing in the clock mesh. Okay. So there would be an extra step, which is if we change the size of a buffer, we might need to resize the clock tree. So that could be a problem. So one of the solutions is to insert dummy capacitance next to the buffer, so that the clock tree delays are not impacted, and we still have our delay estimation accurate. So the first technique was called the M-size technique. It tries to attenuate the size of the buffers that have arrival time that are farther from the mean. The idea is very simple. So basically, we have a distance of the delay of a buffer to the mean arrival time, and then we just linearly decrease the size of the buffer up to the maximum attenuation. So the other technique was called the P-size. It's a stochastic approach. So we also need to define what's going to be the maximum attenuation. So let's see. So we need to go and compute the base arrival time distribution. So we compute the mean over all the distributions, and we compute the mean standard deviation also. So based on that, the idea is that through a threshold value, we compute the area of the delay distribution of a given buffer that is within the threshold, and use that to make the attenuation in an analogous way of what we did for the M-size algorithm. So we, instead of comparing only the mean delay, what we are comparing here is the area of the Gaussian distribution that falls within this threshold. I'm missing some figure here. Apologize for that. So the idea is the same. It's just going to be a linear reduction, but it's taking the area instead of taking the mean. So we made some experiments here with random generated circuits. The arrival times, they were modeled as Gaussian distributions, and we evaluated the 3 types of scenarios: one type with a large input skew, one with a typical, and one with a low input skew. So for all experiments, we assumed 1 gigahertz clock frequency. So this is the result. So we could see, sorry. So we could see that the technique is able to provide improvements in. So by the way, this is for the typical input skew scenario. So we can see that the technique is able to provide improvements in the power consumption and in the clock skew and clock slew. So okay, I have some data to highlight here. So we can see that the benefits are larger for smaller die areas, and that goes in line with what we saw before. So the larger the resistance between 2 buffers, the smaller is the impact of the technique, since it's relying on the short circuit current, and the short circuit current will be reduced for larger die sizes. So the other thing we found was that the denser the mesh, the more improvement we get. Same idea as the die area, so the buffers are closer together. And the other thing we saw was that the more flip-flops we have, the smaller is going to be our improvement. I believe this might be because we are putting more capacitance in the design. So and we are reducing the driving strength. So this might spread the delays a little bit more. Okay. So here's the summary of the power improvement for those 3 scenarios that I mentioned: the high skew, typical, and low, for the 2 algorithms. So we can see that the P-size algorithm slightly overperforms the M-size. So this is the improvement to the clock skew. And this is the penalty in the clock slew. So since we reduced drive strength, it's expected that we will see larger transition times. And okay, so this shows how much we were able to reduce the size of the buffers. So this, the reduction of the size of the buffers is something that was not explored in my thesis. So basically, we could try to take advantage of that by, instead of adding dummy capacitance to avoid impacting the delays of the clock tree that is driving the clock mesh, we could try to take advantage of that by using that to reduce the delay of slow paths in the clock tree. And therefore, besides of reducing the input skew applied to the clock mesh, we would be reducing the power consumption also, because we would pad it with smaller dummy capacitance. But this was not explored there. So again, this is a summary. I'm really short on time, so I still have another technique to talk about. So let me talk about the new clock mesh buffer design, which is the second technique for optimizing the clock meshes. So if we look in the waveforms for two clock signals, and let's say that those clock signals, they're applied to a clock mesh, during the time that one of the signals is connected to VDD and the other is connected to ground, that's when we have the short circuit current spikes. So the idea here is, how can we reduce this current? So the proposal that I made was to, instead of switching the buffers from 0 to 1 and 1 to 0, if we switch from 0 to a high impedance state, and then 1, and then 1 to a high impedance state, and then 0, we would completely eliminate the overlap, the time that one clock buffer is driving a 1 and the other one is driving a 0. And by doing so, we would reduce the short circuit current. So we can do that by implementing a break before switch inverter. So we would have to delay the 0 and 1 signals differently for the P transistor and the N transistor. So for the P transistor, whenever we have a 0 at the clock line, we want to delay that, and a 1, we want to propagate that as fast as possible. And the opposite is valid for the N transistor in the mesh buffer. So the waveforms, they would look like this. So if we look at the signal applied at the gate of the PMOS transistor, it would stay a longer time in 1 and a shorter time in 0, while the N transistor gate would have a longer time in 0 and a shorter time in 1. And in the output signal, we would then create this high impedance time. So for sake of experimentation, we have artificially created this this high impedance time by splitting out the gates of the NMOS and the PMOS transistors, and perform some experiments with that. So what we can see here is how much power we consume for different input skews and different high impedance times. So the first line here, the blue line, is if we don't apply any high impedance time, so that's the baseline. The second line is if we apply 20% of clock period high impedance time. The green line, 40%, and the blue line is 60%. And this over different scenarios of input skew. So we can see that the power consumption increase that we see when the clock skew is applied to a clock mesh is almost fully eliminated if we apply this technique. And this is simply because the power consumption was coming from that short circuit current. But the most interesting data is this one. Besides of improving the power consumption, we are actually improving the clock skew, which could be a little bit surprising. So again, those are the same scenarios. We can see that in the case where we don't have any high impedance, that's when we get the most skew. And once we start to add some high impedance, then we see a smaller clock skew. So this is explained by the fact that if one buffer is driving a 1 and another buffer is driving a 0, then the circuit will converge to whatever of those two buffers has more driving strength, right? And it's not necessarily a good thing. It's better than having just the late buffer switching late. So we are kind of making that when the late buffer switches, we already have a little bit of charges in the load of that buffer. But better than that would be a case where if when a buffer starts to switch, it doesn't find any resistance from whoever is late. And that explains why we are seeing a smaller clock skew. So this also, for the same reason, it also leads to an improvement in the clock slew. So the greatest challenge with this idea is how do we implement that? So for the sake of experimentation, I've manipulated the length of the channels for some of the transistors there to try to delay the signals in a convenient way to create the high impedance time. And this is the data that I got. So we can see that with that design, we can still see benefit in terms of power consumption, but now we have a penalty that we are paying in low skew scenarios. So skew also improves with this buffer model. And clock slew, it is improved only in the cases where we have a larger input skew. So again, because we are delaying the signal through larger channel lengths, we are actually degrading a little bit the clock signal also. And that's translated into this increase in clock slew for low input skew scenarios. So this is the summary of the contribution. So the new buffer design can reduce the power for up to 59% and skew for up to 63%. And it also improves clock slew. So conceptually, there is no overhead in the methodology. The thing is, we would need to find a way to delay the signals conveniently. We can probably find a better buffer design than the one that I've proposed in this work. And the main thing is that we will see larger benefits for cases where we have larger clock skews, which is the scenario in which you probably need to have your clock mesh. So this is the conclusions and future work. So we did in this work a bibliographic study that shows that clock meshes are used to reduce clock skew due to variability, and we have shown what's the benefit of mixing up the clock meshes with clock trees. We have presented the sliding window scheme to enable the simulation of large clock meshes, and we have also proposed 2 algorithms to optimize the clock meshes. So, and that was an improvement with respect to related works where it was always assumed for simplicity of modeling that the clock signals were fully synchronized at the mesh buffer inputs. So with the buffer sizing, we were able to improve the clock mesh skew and power at the cost of clock slew increase. And the new mesh buffer model allows us to improve all the metrics. So those are some ideas for future works. I unfortunately never really got to those. So there were other ideas to optimize clock meshes. So this was actually the topic for a master dissertation by Guilherme Flack. It wasn't necessarily this, but we he did a work where he was trying to optimize the placement of the mesh buffers by moving them over the mesh lines, and he was able to again improve the clock skew and power consumption with this technique. Yeah, here's a little bit more detail on this, and that's all I have. So I guess we are now open for questions.
So please do your questions using the chat channel. So it's time for questions and answers. So so thank you very much, Gustavo, for this nice talk again, and nice work you have done. Also, if you want to read more about the work done by Gustavo, his thesis is available in the Loom system of Federal University of Rio Grande do Sul. And also there is a large paper in the 2 dice transactions on CAD of ACM. So everybody knows by 2 dice. So there is here a question by Anyanda Sundardar, whether introducing high impedance state would blur the definition of the clock edge and causes time uncertainty.
That's a good point. So that goes back to that result slide. So if I understand the question correctly, is at the time that we are now in high impedance state, we should not see transition time as quick as we would get if we didn't have the high impedance time. So that is true if you didn't have the short circuit current, but what ends up happening in the end is that, so let's analyze the clock slew. So if we have a high clock skew in the input of the clock mesh, then the transition time at the output of the clock mesh is going to be determined by the short circuit current that is flowing through the buffers that are in 1 versus the buffers that are at 0. So and at the time that we add the high impedance time, we are reducing that current and we are making the signals to flow smoother from 0 to 1. So it's actually making the edge sharper because it's reducing the slew. I think the part that is less intuitive is why we don't see an overhead here when we have a low input skew. So imagine that you have all the buffers that are switching from 0 to 1 at the same time. So, and now you add a high impedance time before the switch. So in that case, we would not see an impact in the output slew because we would still see all the buffers switching in 0 to 1 at the same time. It's only that now they are going to switch before some time in which they spend into this high impedance state. So what the experiment shows is that we do not get a degradation of clock slew.
Okay, there is a question by Almas Shati. 20% skew is an indication of process variation. And the second one, why not use useful skew as it washed away by variability?
Okay, so yeah, the first question, the 20% skew is an indication of both process and environmental variability. So from my experience, I don't have any number to quote here, but the main source of clock skew is the environmental variability, so mostly power supply. So when the power supply is switching and the circuit's operating with different temperature gradients, you may get large clock skews. So the process variability also impacts but I believe that the highest source of input skew is going to be the environmental variability. The second question was, why not use useful skew? I'm not sure if I understand the question though. So when you apply clock mesh, the clock mesh is averaging out the arrival times of all the at all the sinks based on the arrival times at the mesh buffers. So it wouldn't be possible to have the mesh insert some useful skew into the output sinks.
So also would like to thank Ninja for her question, and she's saying that she's from India Institute of Technology, Kharagpur, India. And Almas, the last question, he's from Library Technologies in California, and he has another question: how much is temperature gradients?
I don't know. I don't know. I think this is it varies a lot from the assumptions made in the characterization of the clock network. So I'm sorry, I don't have any data that I can quote. The only thing that I do remember from my experience analyzing scenarios was that the power supply noise was probably the biggest source of variability in the clock delay.
So another question by Almas: how much is voltage jitter?
How much is voltage jitter? Voltage, you mean okay, so jitter, as I define it in this work, was the variation of the arrival time for one specific clock sync over time. So the jitter tends to be much smaller than the clock skew, from my experience again. And I mean, I feel very reluctant in citing that because I haven't been having access to any data on clock designs for a while now. But at the time that I was working more closely to that, I remember that jitter tended to be small compared to the clock skew. And the other thing is that the clock jitter actually has a very low frequency, in the sense that from a cycle to cycle, the variation of the clock delay is not that much. It varies more over time. So so the main problem with jitter is the cycle to cycle jitter, because that can impact the clock period. Because if you look at the equation to define the clock period, you need to give time for, actually, let me go back to the beginning here. We need to have time for the clock to propagate from the first sequential element to the last one. But the interesting part is that the propagation starts at the clock edge n, and then the data is read by clock edge n+1. So we need to directly account cycle to cycle jitter in the clock period because of that. But as I was saying, the cycle to cycle jittering, from what I remember, used to be very small.
So another by Almas, cycle by cycle relative voltage variation.
Cycle. Oh, if the cycle to cycle jitter is relative to the voltage variation, I would think so. Yeah, because the power supply noise can be very high frequency, so it may really be one of the main sources of contribution to cycle jitter. But again, I'm not talking based on any data that I've seen.
Okay, so I have a question also to Gustavo. So what is your view about clock distribution in recent technologies like FinFETs and FDSOI?
Well, that's a good question, and I don't have a good answer for it. So I think clock distribution in the past years changed a lot, but mostly because we have very tight power constraints these days. So I don't know what's the impact of new technologies in changes to those to the clock architectures themselves. I think there will always be a niche for high performance clock distribution. So clock meshes, they will be there, but in the regular circuits that we see today, for mobile applications, usually I wouldn't expect to see a lot of clock meshes in those designs just because of the power consumption implications.
Okay, so there is another complement of questions by Almas. Are you saying that guard band shouldn't be 20%? Did you use Monte Carlo for variations?
Yes, I did use Monte Carlo for variations. So I don't know what the guard band should be. The 20%, I got the number at the time from the literature and from some data that I had from circuits that I was working on. But I don't know what this number is today. But I think the idea of analyzing the clock network is that you want to be able to get as accurate as possible analysis so you can reduce the guard band.
Okay, thank you very much, Gustavo. So we have no more questions. Thank you very much for your nice talk. I hope to see you in person in the near future.